Good morning, everyone. It's a pleasure to have Emilio Minicello back here to tell us more about coverages and Grothendieck Toposes. Thank you, Emilio. The floor is yours.
Thank you, Mahmoud. Okay, so today I'm going to finish off this little mini course we're doing on coverages and growth and Toposes. I'm just going to say I might go over today, so I'm going to try and keep it to 11:15. I will not be offended in the slightest if you leave. Um, so just wanted to make that announcement because we've got a lot to get to today. All right, so we're going to pick up from where we were last time, which is talking about set theory. So last time, I explained what Grothendieck universes were. You can think of a Grothendieck universe right now, rather than going through all the definitions again. You can think of a Grothendieck universe as a set that's big enough that any operation you do on sets inside of it, any set theoretic operation you do cannot leave the Grothendieck universe. Power sets, products, functions, unions, you can't get out of this set
Right,
using
but just
any of those
right,
operations.
but just to be clear, that means yes, operations on elements of you, not operations on all of you.
Exactly. Good. We're going to fix two Grothendieck universes that are nested. We're going to call them U and V. Elements of U we're going to call small sets. Elements of V we're going to call large sets. And any set that's outside of that's not in V, we're going to call very large. Um, if it's not large. Okay. So that means U is a large set and V is a very large set. These sets cannot contain themselves. Okay. Okay. So now we have everything we need to talk about small and large categories. A category C is small if the set of objects and the set of morphisms are small sets. And here, when I say the set of morphisms, I mean take the union overall pair of objects, and they're Hom sets. And then similarly define large categories. We say a category is locally small if for every pair of objects, the Hom sets are small. So there might be a large set of objects, but each Hom set is a small set. Okay. We say C is essentially small if it is equivalent to a small category. Okay. Um, so example, let's set denote a category of small sets. Um, this is a large category that is locally small and is not essentially small. Okay. Um, the category of
Is
categories.
it obvious that it's not essentially small?
So if it was essentially small, it'd be equivalent to a small category,
Mm-hmm.
right?
Mm-hmm.
Um, so that means that you would have, um, yeah, maybe it's not obvious.
Well, I guess one thing you can say is with set, if I want to essentialize, I look up the isomorphism. All I care about is, the cardinalities
Right.
of the sets in it. So I can skeletonize to say, well, I can go all the way to saying I have one set for each cardinality.
Yeah, I think if it's essentially small, then you could find a skeleton that's small. Is that right?
Yeah,
Um, and then in that case, that's impossible because there's too
correct.
many isomorphism
Yeah,
classes,
yeah.
right? So that's the reason. And then for similar reasoning, so are cat uh, small categories and topological spaces, right? Because every set can be seen as a category, every set can be seen as a topological space. Okay. But they are both locally small. Okay. Next example, the category man of finite dim smooth manifolds is large, but is essentially small. One way to see this is by using the Whitney embedding theorem.
How about topological manifolds?
You're ahead of me, Mahmoud. We'll get to that next. By the Whitney embedding theorem, every smooth manifold is isomorphic to a submanifold of R infinity. Um, but the subsets of R infinity are a set, a small set, and therefore um, the category is essentially small.
By the way, I realized a very simple way of seeing that thing about set that you were asking about a minute ago.
Okay.
Well, let's just take the simplest case where my lower universe U is just the countable numbers. So I take finite sets. Well, I have an infinite number of finite sets. Cardinal is 1, 2, and n. That's not a finite set.
Mm-hmm.
So it's not
Oh, I see what you're
small.
saying. Yeah, yeah, yeah. Right. So then that can
Let's
never
look at the
be
simplest case.
essentially finite, right?
That's right. And then the same argument with some other cardinal will go for any size U.
Exactly. Exactly. Good point. Okay. So that's smooth manifolds. However, it's a little unsatisfying because the Whitney embedding theorem doesn't apply to other kinds of manifolds. So now let's prove it for topological manifolds. And now we have to be a little bit more clever. Well, maybe not more clever, but more careful. So this is a category of finite dimensional topological manifolds and continuous functions.
The manifolds are just pieces of Rn glued together by things. So
That, exactly. So that's what we're going to use here. Um, now, um, fact, topological manifolds can only
Right. And there's also
have
a fact that usually require to have a countable basis. So you're starting with countable there.
exactly. So topological manifolds can only have countably many connected components. Otherwise, they would violate second countability, right? And each component is path connected, right? Now, so I'm just going to give the references here. You can find them in the notes. There are some nice Math Overflow answers. So by this, every connected top manifold has cardinality at most the continuum. And the continuum we write as C, and that's the same thing as 2. Aleph null. I'm terrible at drawing it. Let's try like God.
Well, yeah.
To an end. And that's the cardinality of the real numbers, right? Okay. So that means every connected topological manifold has cardinality at most R, right? So Rn has the same cardinality as R. Okay. So then, hence, by another answer, assuming the axiom of choice, of countable choice, the cardinality of M, so topological manifold M, yeah, cardinality M, top man, is at most also the continuum. So the idea there is that you do some cardinal arithmetic, you start off with a countable number of continuums, and then you can manipulate that down to just being the continuum. I'm not going to go too much into it, but the cardinality of every topological manifold is at most the continuum.
Right. Well, but one thing you can mention is that with cardinals, once you get to infinite cardinals, the product of two cardinals just winds up being always the bigger cardinal.
Right. So the point is that what you do is you take like C times Aleph null. That's just C. Right. So that's the argument why it works. Okay. All right. So so the cardinality of every topological manifold is at most C. So that means, suppose I have a set there are so for each set of cardinality at most C, there are at most 2 to the C topologies on X. Certainly there are less, right? Because you don't just take all subsets, but certainly it's bounded by all subsets, right? So if I have a set of cardinality of the continuum, there's only 2 to the C possible topological manifolds I could put, topological manifold structures I could put on that set, right? If it had cardinality greater than the continuum, I know I can't put a topological manifold structure on it. Hence, there can be at most 2 to the C non-isomorphic topological manifolds. Hence, top man is essentially small, using the axiom of choice to choose a skeleton, to choose a topological manifold from every isomorphism class. And now we really see why we need the Grothendieck universe axioms, right? Because C is a small set, and therefore, by the Grothendieck universe axioms, its power set is a small set, right? So that means that um, the cardinality of topological manifolds, the set of objects, is at most 2 to the C, and that stays as a small set. Okay. So category of topological manifolds is essentially small. Nice fact. Didn't use any Whitney embedding theorem, didn't use anything.
Can
Okay?
I try something?
Sure.
You see, if you have a manifold, you can choose an atlas. And then once you have the atlas, you can look at the transition functions. But think of the transition functions as the following. You have two piece of CN, two open sets, and from a little piece of this to a little piece of the other one, there's a gluing map.
Mhm.
Isn't it true that if you take the disjoint union of this target of all these charts and then put the relationship that 2 points are the same if they are related by a transition function, if you do that topological space, you get something that is homeomorphic to your manifold?
If I take so you fix an
Fix an
atlas,
atlas.
take every chart and
Take
and glue
every
them.
chart, look at the images, the
Uh,
targets. Those are a bunch of open sets of Rn. And now the transition function glues a piece of this to a piece of that. So put an equivalence relation on the disjoint union. The two things are the same if that happens.
right. Yeah. Okay.
So that means that every manifold, not every manifold is built out of these things.
And
Bunch
they
of
have
bunch,
cardinality.
bunch of
The
pieces of
um,
CN and bunch of maps, and everything is within
right.
sets. So that's a quick proof, isn't it?
The quick proof. That's it.
Well, right. But either way, the general thing behind both proofs is I say, here's some data that I can use to specify a manifold, whether it's topology or you're gluing, and then you say, then I do my usual counting and estimating to bound the cardinality of all the different types of
By the way, I think I'm
data
not even
sets.
using second countability in this argument. It's true for non-second countable.
Well, but then how would, but if you didn't have that, right, then I
You
could
could
have
have
things like a
points,
long line with an arbitrary cardinal in it that would certainly defeat it.
right? I could take any set as a discrete
No, but
zero
it's
dimensional
still a
manifold.
set. Still a set. I'm
Yeah,
not,
but it could be bigger than the Grothendieck universe. So it depends how you want to do it, right? Uh, if it's not second countable,
yeah.
then you have no bound on the cardinality of your manifolds.
Okay. All right. Maybe we can
If you
talk.
want them, if you want to say like, oh, I only want to consider topological manifolds with whose underlying set is small, then you're good, right? Um,
Yeah, something like that. Yeah.
something like that, you should
But
you should
it can be beyond second countable. That's what I'm saying.
yeah,
Yeah.
yeah.
But it has to be some bound on it.
You
Yeah.
have to have some
Otherwise,
bound,
you get it.
Yeah.
Otherwise, you get the same
But
problem we had with sets. The set of category of small sets not being essentially small.
exactly.
okay.
Otherwise, you
I
repeat
would
that same problem.
Yeah. I would like to make that into a very precise proof though. I think it's easy. It's very
Okay.
intuitive. And it actually goes to the heart of what a manifold is.
Mm-hmm. Okay.
Because there are
Uh,
more such things than manifolds actually. Like
sure.
orbifolds are the same way. So
Right.
this includes things that are not even manifolds, but definitely manifolds are among these gluings.
Right. Right. Yeah.
Anyway, it
Yeah.
relates to stuff that Shane and Thomas and I are talking about. Okay. Anyway,
All right.
thank you.
So now this proof lends itself to proving also, that smooth manifolds and complex manifolds and whatever other manifolds you want to consider also are essentially small. So let's argue that now. So now I want to argue that smooth manifolds are essentially small, not using the Whitney embedding theorem. Okay. Now, a finite dimensional smooth manifold M is a topological manifold with a smooth structure, right? What's a smooth structure? So we want to show there's a small set of isomorphism classes of manifolds. So smooth structure consists of an equivalence class of atlases, right? So a smooth atlas A of M consists of a set of topological embeddings such that the transition functions are smooth. Right? In which case we say phi I, phi j are compatible. Whoops. Sorry, Grandma. All right. So two atlases are deemed equivalent. Two atlases are deemed equivalent if every pair um, are compatible. Okay. So smooth structure is an equivalence class of atlases under this equivalence relation. Um, so using the fact that every manifold M is second countable, every atlas is equivalent to a countable atlas. Okay. So the isomorphism type of a smooth manifold is completely determined by its underlying topological manifold and a countable atlas. Okay. So there are precisely C to the C many functions from Rn to M. M is a, a smooth manifold. Hence, there are at most this many distinct smooth atlases on a topological manifold. Where, remember, omega here is the cardinality of the natural numbers, right? So it says, okay, I have a topological manifold. It has cardinality C, and a smooth atlas, at least an isomorphism type of a smooth atlas, an equivalence class, is at most countable, right? So it's equivalent to a countable atlas. So that means I take countably many There's at most countably many like functions from Rn to M, right? Um, and hence, there are at most omega times C, which, as Ray said, is just the maximum, which is just this many non-isomorphic smooth manifolds. Okay? Hence, man is essentially small. And the same argument works for complex manifolds, right? Really any other kind of manifold you can think of. Okay. All right. So from there, we've proven that topological manifolds and manifolds are essentially small. Now I want to talk about why we care so much about smallness. So let's say proposition. If so we'll do it like this. If C and D are small, then the category of functors from C to D is small. How do you see that? Well, I want to see that the set of objects here is a small set. Well, what are objects here? They're a set of functions from the objects of C to the objects of D satisfying a property. The set of functions from a small set to a small set by the Grothendieck universe is a small set. Hence, the objects are small, and then similar argument tells you that the set of morphisms are small. Okay. So if you have two small categories, the category of functors between them is a small category. If C is small, D is locally small, then fun CD is locally small. So if I have a small category and I take the category of sets, that's a locally small category. So the category of presheaves on any small category is locally small. If C and D are large categories, then by the same argument as the first bullet point, fun CD is large. Okay. Now, if C and D are very large categories, so they're not in the Grothendieck universe, we might not even be able to prove that the functor category on it, any of the stuff inside of it forms a set. Because remember, we have to be able to prove using our formal system that a collection defined by, logic, first order logic is a set. It doesn't come for free. So if you don't have any sort of bounds, you might not even be able to prove that the functor category exists, right? Okay. So this is what allows us to work on small sites because the pre-sheaf category on a small category is always locally small. So on a large category, there's no guarantee. So let me make a remark. If C is large, pre-sheaves on C may not be locally small. Okay. And we know that the category of pre-sheaves on any category is never essentially small because the category of sets embeds fully faithfully into it. And that category is not essentially small, right? Okay. So given a category, so for us, a category, when I say category, I'll mean a large category that's locally small. A small diagram in C is a functor f from I to C, where I is small, a small category. Similarly, if kappa is a regular cardinal, and remember, regular cardinals are the kind of cardinals where, like, if you're less than this cardinal and you take unions and like functions of unions, you stay below this cardinal. So regular cardinals are really useful in category theory because the category of sets of cardinality up to kappa, if it's regular, is co-complete. If it's not, then it's not co-complete, because then you could build out of smaller cardinality sets, you can get out of that cardinality. So similarly, if kappa is a regular cardinal, um, and I has the objects of I and morphisms of I less than kappa, then we say I is kappa small. Okay. We say a category C is kappa co-complete or complete if it has all kappa small colimits. And then we say it's co-complete or complete if it has all small colimits. Okay. So now there's real content to all of this stuff, okay? By the following result of Freyd. This is Freyd's theorem. Let C be a small complete category. So that means it has all small limits. Then C is a preorder. So let's prove that. So suppose C, and this is my one proof of the day. So suppose C is small and complete. Let kappa be the cardinality of the set of morphisms of C. Suppose C is not a preorder. So given two objects, X and Y, there exists some pair X and Y. There exists two distinct morphisms, F and G, from X to Y. Consider the product over kappa of Y. Then there are 2 to the kappa many morphisms from X to the product, oops, of Y, given by sequences A0, A1, dot, 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 with AI in F, G. Since 2 to the kappa is greater than kappa, thanks to Cantor's theorem, this implies the cardinality of the morphisms is greater than kappa. Contradiction. Okay. So that means you have to be careful. You can't just assume things, right? If you have a small category, you can't have all small limits and co-limits unless it's a pre-order. And of course, the same comment works for large categories. You have a large category, it can't have all large limits. Otherwise, it's a pre-order. Okay. Any questions about that?
No?
Okay. So then I will move on now to large sites. Um, I do want to move through this kind of quickly. I just, yeah, what do I want to say? Um, I want to talk about this because it's something that bothered me for a long time. So whenever you look in the literature, almost everybody defines sites on a small category. But, what about large categories? There's lots of large categories that we care about in geometry. Like the category of topological spaces is not essentially small. There's nothing you can do. Right? It is if you build it out of small sets, it will be an essentially large category. Okay. So I want to talk a little bit about what goes wrong if you consider large sites and how do we fix it. Okay. So first thing we need to do is just copy over all of the definitions from previously to large categories. So a large collection of families on a category C consists of a large set J of U, whose elements are also large sets, are large families of morphisms. Right, so now you let this indexing set I be large. All the other definitions we talked about so far poured over just as before, right? All other definitions still make sense. In particular, pre-sheaves and sheaves and all of that still makes sense, right? Um, so we call CJ a large site if J large coverage, which is a large collection of families that's also a coverage. And C is large and not essentially small. Okay. Okay. So nothing has gone wrong so far, right? So the category of sheaves on a large site exists. So then let's see some examples of large sites. So example, so we can have set and J epi. So this is the site whose underlying category is a category of sets, and then a covering family is one that's jointly epimorphic, right? So if I take the union of their images, it covers the set. So this is a large set, is a large site. Category of topological spaces, and the typical coverage there is large. Now, there's one really interesting example I just want to mention quickly, and I'm not, super familiar with this, but I found it really interesting. There's something called condensed sets, and this has kind of been making the rounds in arithmetic geometry, and algebraic geometry. Um, this actually forms a large site. So this actually is an instance of something that's actually really useful, really popular in today's in um, you know, algebraic geometry, and yet it is not a small site, and this causes annoyances with people, and I've read online people being very confused about this. So let's talk about that for a second. Um, so let pro of finset denote the category um, the category of functors P from finset to set that are co-filtered limits of representables. I won't explain what that means right now. We'll talk about it more later. Via something called stone duality. This is equivalent to the category ST of stone spaces. These are spaces that are compact, Hausdorff, and totally disconnected. Okay. Now, the category ST is essentially large. Okay. Why is that? I don't remember why, but it is essentially large, right? Because the category of topological spaces. So, and you just have to check it's compact, Hausdorff, totally disconnected. It's an essentially large category. So basically, what you see in the literature is two solutions, or two ways of getting around the idea. Okay, so this is what Schulze does. So Schulze is the Fields medalist in algebraic geometry, arithmetic geometry. So he uses this site. Okay, so what Schulze does is he defines, so he fixes an uncountable cardinal kappa and lets ST kappa denote the full subcategory of stone spaces with cardinality less than kappa. So each of these guys is a small site. And the cardinal obviously has to be in U. It's a small cardinal. So this is a small site. And then what he does is he gives it a coverage. J, and it's actually a Grothendieck topology called the coherent topology. Um, considers a cover.
Can I ask you something? I think it was explicit because you're going back and forth between them. The way you go from a set, stone space to such a functor is by mapping finite sets to it, or
Be honest, I don't know. I haven't actually like looked into this too much. I just like that this is an example of
okay,
the large site stuff.
okay,
If anybody knows more about this, please chime in.
okay.
Um,
Because you
so then
talk about cardinality of something, you define them as functors from fin set to sets. So, but then you say,
satisfying a certain property, yeah.
but then you talk about
But the point
cardinality of
is,
such things.
is that the category of functors is a large category
Mm,
because set is a large category,
yeah.
right? I could take the constant functors. That
Mm.
gives me something that's a large, right? Um, okay. So then what he does is he sets CK equal to the sheaves on this small site. Um, and then he takes a colimit over these cardinals, and he says that is the category of condensed sets. Okay. Problem. This is not a Grothendieck topos. There's no small site whose sheaves are equivalent to this category. Okay. So that's how Schulze gets around it, but there's a trade-off. You don't get a Grothendieck topos anymore. Somebody else, Barwick and Hein, so alternate solution. And this was, I believe, done independently. They define pyknotic sets. And I should say a word about like the motivation here. The motivation here was that they wanted a convenient category to talk about functional analysis. And they wanted to be able to mix functional analysis and homological algebra. In particular, they wanted an abelian category of like uh, uh like sheaves of vector spaces or something like that. Um, so we saw Schultz's kind of ad hoc solution to the problem we talked about. Now, Barwick and Hein come up with a different solution. Um, they do the following. So they fix three Grothendieck universes: little u, big U, and big V. Okay. They fix three Grothendieck universes, call sets in little u tiny. They define uh, stone of U to be category of tiny stone spaces. Well, this is a small category. Hence, they define this to be the category of pyknotic sets. And it turns out that there are actual differences between these two constructions.
What are those two letters inside, those two things inside sheaf?
This is the
ST sub,
category of
uh-huh.
this is the category of tiny stone spaces.
Yeah, the other one?
This is the coherent Grothendieck topology on that category. So I haven't defined that,
Ah,
but it's
okay.
just some coverage. Okay. Um, okay, good. This is a category of pyknotic sets, and there are actual differences. Um, it actually has consequences for the theory. So, like this set with the indiscrete topology is pyknotic, but not condensed. Okay. So the reason why I'm kind of harping on this is that like this is real. This is like things that you have to care about. As much as everybody loves to just throw this stuff under the rug, there are consequences. All right. Okay. All right. So
And
those are
this
some
is also
examples.
interesting because this is showing a real life example where it's useful to go to three levels of universes.
Right. Right. Exactly.
'Cause,
Um,
in
good.
general, what happens, yes, things get big, you might have to go to a higher universe, and here's one where it's actually useful to go to three.
Right. Right. Okay, so now I want to talk about what goes wrong. So let me maybe just say this in words first. So suppose I have a large site and I take sheaves on the large site. That exists. It's a category. It's a large category. It's not necessarily locally small. So I'm looking at pre-sheaves and I want to do sheafification. So I haven't talked about sheafification yet, but hopefully you've seen it before. Sheafification is a functor from pre-sheaves into sheaves. And what you do is you take a colimit. You have to take a colimit over covering families. Now, if you have a large coverage, that means you could be taking a colimit over a large category. Large categories do not have large colimits in general. If a large category has all large colimits, by Freyd's theorem, it's a preorder. Okay. Therefore, sheafification does not necessarily exist on large sites. So, problems with large sites. Sheafification, sheafification does not necessarily exist. There's no reason that a large category, even if it has all small limits and colimits, should have any large colimits or limits. Um, Another problem is think about the following. I want to consider the category of pre-sheaves on my category, right? If the category C is small, I take pre-sheaves on that. I get a large category, but that large category is Cartesian closed, right? So Cartesian closure is a very, very important part of being a pre-sheaf category. I take two pre-sheaves and I want to consider their internal Hom. So I have X and Y, and I take internal Hom XY, right? That's a pre-sheaf. How do you define that pre-sheaf? You define it like follows. So let me just write this in blue over here. So if I have X and Y are pre-sheaves, then their internal Hom, Y to the X, is also a presheaf, and it's defined by on a U in C, it's given by taking presheaves, take the representable on U, multiply it by X, and map it to Y. Okay, this is how you define Cartesian closure of presheaf categories, right? But there's a problem. There's a problem because what happens if this category C is large? Then we know that the presheaf category is not necessarily locally small. In other words, this set might not be a small set. Therefore, this is not a functor from C to small sets. Therefore, it's not a presheaf. So in other words, summarizing is not necessarily Cartesian closed. Okay. This also implies, of course, that presheaf categories might not have subobject classifiers, right? Because subobject classifiers, all that stuff is built out of this Cartesian closed structure. So these are two big problems with working with large sites. Sheafification might not exist. Presheaf category might not be Cartesian closed. Now, if you don't care about either of those things, you're good. You can keep doing whatever you want to do, right? But large amounts of mathematics really rely on these two things existing, right? Okay, so now there are some workarounds.
Now, you were also saying, you may have said this, when you say small sites, is there a distinction between essentially small and small, or essentially small is just as good as small?
Yeah, let's just identify them with the we'll just use the equivalents,
Okay.
right? And we'll just define the pre-sheaf topos on this thing as okay, go over by the equivalents, take that, and then you know, yeah. So let's not worry about that difference.
Okay.
Um, okay, so there are some workarounds. So I'm not going to describe this right now, but there are two workarounds called whisk and what are called small presheaves. And I'll just say what I don't like about them. Whisk requires you to restrict the kind of covering families that you consider. So you want your covering family, you want there to be a small subset of covering families that's cofinal in all of them. So this is technical and requires um, a property on the coverage. And in particular, um, there are several examples of sites, large sites that don't satisfy whisk. So let's say see David Roberts's paper. Roberts, 2012, for this. He has a really lovely paper where he talks about all of these issues. With whisk, small presheaves, you restrict the kind of presheaves you're going to talk about. So now I don't want all presheaves. I want only those presheaves that I can write as colimits of small colimits of representables. Okay. Problem is, um, so let's call this the category of small presheaves on C might not have all limits. Okay. So that's annoying. It might not even have all small limits. Okay. Now the third solution is my favorite, and this is one that Mahmoud has actually used in one of his papers, and also what Barwick and Hine have used. So we call this the very small Grothendieck universe. So the solution is fix three Grothendieck universes. Build C, build your site using tiny sets. Then the category of pre-sheaves on it will be small. And then you're done, right? Now, of course, there's a disadvantage here in that now you have to do more bookkeeping. Have to do more bookkeeping, right? Because you can never say like, okay, I'm going to build a category of topological spaces on tiny sets. So I build that, it's fine. It's a small category. But of course, that category doesn't have small limits and co-limits anymore, right? It only has tiny limits and tiny co-limits. So now, anytime you want to talk about anything you're doing, you always have to be really careful. Am I talking about tiny sets, small sets, large sets? And it'll introduce complexity into your work. Okay. However, I think that this is probably the most used technique in homotopy theory, at least. So I've seen this used by Barwick-Hein. I've seen it used by Mahmoud in his paper. And I've seen it used by Jardine in his paper as well. So this tends to be kind of the most used solution to this problem.
Emilio, can I ask about the
You
whisk
should,
thing?
yeah.
Sure.
So, for example, if I take smooth manifolds and I take covers, like I define a coverage by just taking the one that's usually used for topological spaces, and you just take literally
Open
open
covers.
subcover, yeah, open covers. This already has the smallness to it,
That satisfies whisk.
right?
So on
And then
top,
even if I
the
did,
category topological,
sorry,
huh?
Go on, sorry.
Oh, category of topological spaces with the open cover coverage is a
Yeah,
large site that satisfies whisk.
okay. Okay, but it satisfies whisk or the thing is already small?
It's not already small. It's an
Okay,
essentially large category and it's a large
got it.
site,
Okay,
but it satisfies whisk.
thanks.
That was kind of the motivation, I think, for using whisk in this context was to get that. But there are other sites that are large that do not satisfy whisk. They're complicated, but they
Yeah,
exist.
I just noticed that searching Robert's paper real quick for the word manifold, I couldn't find it.
Um, yeah, I think it's
So
mostly
I didn't know what the what like what relevant problem
well,
using
for
what, like, you know what I'm
manifolds, it's
saying?
already small. For manifolds, the site's already small, right?
Right.
That's what we proved. So you don't have to worry about
But
any of those.
you could take the site of like open embeddings and that might not be small or that thing's small too.
The category of open embeddings of a fixed manifold,
I guess that's what you're doing because that's what you're taking colimits over anyway when you, so you're saying that's already small?
yeah,
Okay, cool.
yeah, yeah, exactly. Okay, cool. All right, so that is the solution to that. I really just wanted to say that because it's something that's bothered the hell out of me for years now. But now we're going to move on. So are there any questions about that?
No, at some point you should explain to us how we use that in our work. Yeah.
Well, you've already done it, right? You take, I want to define sheaves on some category, right? But my category is large. So what do? Well, I look at my category and I see how it was constructed. If it was made using mathematics, it probably has an underlying site somewhere. I build it out of sets somehow, right? So instead of taking small sets, I take tiny sets. I
Yeah.
build my category out of tiny sets, right? So think about like smooth manifolds or topological spaces or whatever you want to do, right? You take tiny sets and you redefine it, right? Now you have a category that is small. You've cheated. You've cheated, right? You've pushed everything down a level,
Yeah.
and now you have a smaller world. So then you get to keep all the classical world in small sets, and you've pushed everything down. So now you can talk about sheaves of small sets on a tiny category, and then you can keep going and move on with your life.
Yeah.
But now, of course, you've introduced additional complexity into what you're doing. And you have to be careful, right? Because now the site is living in almost a different universe, right?
Yeah.
Right, and this is the way these things often happen, that you have to sometimes, yes, you want to do something, but you find out that will move you up universes. So,
Exactly. So taking like pre-sheaves, that moves you up a universe.
yeah.
Okay, good. All right, so now we're going to switch gears and talk about localization. So it's 10:09, so I've got an hour. So let's see what we can get through. Um, I want to talk about localization, and then I want to talk about presentable categories. Okay. Um, so let C be a locally small category. And let W be a subset of the morphisms of C, and let this be a large set. A localization of C at W consists of a functor L from C to D such that 1, L inverts W. So L takes every morphism in W to an isomorphism. And for any functor F from C to E that also inverts W, there exists a functor F tilde from D to E and a natural isomorphism eta from F to F tilde L.
So just
So what
to
does
be
that
clear,
mean?
for now, it looks like we left the sites and that on the back burner and just going to talking about localization for a
Exactly,
bit.
exactly.
Okay.
So now I say that this functor here is a localization if it inverts W, and for any time I have another functor F that also inverts W, then there has to exist a functor F tilde and a natural isomorphism uh, like this, right? Or maybe I'll write it like this.
One of the
And
most profound
finally,
ideas in math.
yeah, absolutely, absolutely.
It's so simple, but it's so it has such amazing ramifications.
Well, you
Yeah.
had the basic version of it in your class with the complex numbers.
Oh, I see what you mean. Yeah, yeah. Yeah, that's true. Um, right. Okay. So now, the last thing we ask for is that for every category E, the functor um, given by precomposition takes a functor from D to E, precomposes it with L, that gives me a functor that inverts W from C to E. I want that functor to be fully faithful. So these three conditions together define a localization of a category.
If it
And
exists.
say it again.
If it exists, right?
So yeah, if it exists, right. So right now we're just saying we're defining a thing. Remark, if a localization exists at W exists, it's unique up to equivalence. Okay. Maybe I'll make one more remark. You can actually define localization using a nice universal property. What you do is you say, so let I be the poset 0 less than or equal to 1, and let J be the walking isomorphism, which means the category with two objects and two isomorphisms, right? So, I mean, one isomorphism, well, two isomorphism, one this way and then with its inverse, right? And then I multiply both of those with W as a discrete category. I have a map that takes W, which is a morphism in C, and it takes the walking arrow and it takes it to that morphism in C. So that's a functor. And here, what I do is I include this map into one of these two isomorphisms here. And then I take a push out. So L is a localization if and only if it's a push out in big cat. If it's a push out like above in cat. So that's a nice way of another way of repackaging everything.
You
Okay.
define W as a category?
Yeah. So W is a discrete category, just a set. Okay. So I mean it's really kind of beautiful, right? You take W, multiply it by an arrow, push that into set. Oh, well, then I take it and I push that down here. And now I think of all of those morphisms as isomorphisms, and then I take the push out. So what does it do? It takes all the morphisms in W and C and it turns them into isomorphisms, right? So that's what localization is. Now there's an actual construction one can do.
Instead of a discrete category,
Yeah.
I mean, you can also, don't you need to take the smallest category containing all those morphisms?
No, because what I want is I want to take a pair, which is a morphism. I want to take something like W, which is a morphism in my category, and I want to take the walking arrow, and I want to map that to the actual morphism in C.
Mhm.
You're
Okay.
basically things W to index those the arrows that are supposed to be inverted.
Okay, okay,
Exactly.
W is just
Exactly.
is basically an indexing set.
okay.
Yep. Yep. Perfect. Now, all I've said so far is if this thing exists and blah, blah, blah. There's an actual construction one can do called a Gabriel-Zisman localization. So its objects are the same, and we denote it Gabriel-Zisman localization of C at W denoted C W inverse has the same objects. as C, but now morphisms are equivalence classes of zigzags.
Do you know what year that paper is?
67, and it's in their book at least. Their book was published in 67.
Okay.
Roland Zisman's book on localization and homotopy theory. Okay. Okay, so you have zigzags where you're only allowed to go in the backwards direction if you're in W, and you take a certain kind of equivalence class on these. And that constructs you a category. And it turns out this is all well defined. So it's Gabriel Zisman, 67, lemma 1.2, lemma 1.2. Says for any category C and large set C, this category is a localization. So you have to still say what the functor is, but it's just taking equivalence classes. Right? So this always exists. However, it's not as useful as it might seem.
It's not locally small, right?
It's not locally small in general. Even, yeah, well, if C is small, then you're fine, right? But we typically want to localize large categories. So that can be a real pain, right? Because if it's not locally small, then pre-sheaves on it are not necessarily locally small, and then we run into all kinds of problems. Secondly, the construction is terrible. The construction is not amenable to actual computations.
Right. Usually in actual practice, we can do it because there's a simplifying thing, some simplifying property lets you collapse the zigzags.
Right, exactly.
Model categories solve this problem, but it's kind of an overkill. Yeah.
There's a whole so the whole subject of homotopical category theory is trying to figure out better models for localizations, and then that gets you to infinity category theory and so on, right? Okay, so I just wanted to say that. So just know that there's always a localization always exists, but sometimes I mean the actual construction is not very nice. A lot of times what you can do is find ways of reducing it, finding different models that are more amenable for computation. That's what actually happens in practice. But you should know that it always exists, at least. Okay, now a definition. We say that a functor L from C to D is reflective if it has a fully faithful right adjoint. So this looks like this. Oops, I have I, and I have L.
Can I ask you one thing?
Uh-huh.
When we say that this is not locally small, of course, when you look at the construction, because you involve objects, then you see that it gets out of hand. But
Yeah,
then you put equivalence relation on them. So you also severely cut it down. So in many cases, it is locally small. It's just that you cannot show it.
right, exactly, right. So like the point is like we just don't know. We just don't know. Like a lot of times, yeah, it could be locally small. We just don't know.
You just don't know. And then if you have some additional structure like some fibrancy, cofibrancy, etc. involved, then the thing that you didn't know, now suddenly you know a lot about it. Like you realize that it all along it was small, locally
Yeah,
small.
yeah, very good point. Yeah, yeah, totally. Okay, so now we say a functor is reflective if it has a fully faithful right adjoint. Um, if I have a full subcategory, with a left adjoint to the inclusion, any inclusion of a full subcategory is automatically fully faithful. So if that has a right adjoint, we call E a reflective subcategory. Let's see. We call curly L, which is I after L, the localizer. So what we're interested in are L functors L that are reflective and that furthermore are localizations. So let me write why we care about this. It's a very nice proposition that you can find in Emily Reel's book, Category Theory and Context. This is proposition 4.5.15, which says if I from E to C is a reflective subcategory, then E has all the same limits as C, and E has all colimits of C. And so this is a reflective subcategory with left adjoint L. Has all colimits of C obtained by computing the colimit in C and then applying L. So what does that mean? It says, okay, I have some reflective subcategory of C. And subcategories can have arbitrarily different structure to the bigger category, right? So you don't necessarily know that it inherits any limits or colimits or anything, right? But if it's reflective, it turns out that the way you construct limits in E is exactly the same as the way you construct limits in C. However, to construct a colimit in E, you first move the diagram into C, take the colimit there, and then apply L. Now you have a colimit in E. Okay. So that's why reflective subcategories are important categorically. Okay. So that's what I wanted to say there. It turns out, so another proposition. So if L from C to D is a reflective functor, so that means it has a fully faithful right adjoint, let W denote the class of morphisms. And for me, class is the same thing as large set. A class of morphisms inverted by L. Then L is a localization of C at W. So anytime you have a reflective functor, you automatically get a localization. So in other words, D is equivalent to C inverted at W. Okay. Right. Okay. So what more do I want to say about that? I think that's good. Right. Okay. So that's that. Now all right, so we have 30 minutes left. So now I'm going to start talking about locally presentable categories. Okay. So how do I want to start talking about this? So I know there's lots of moving pieces here today. That's why I wanted a little bit of extra time.
So maybe you said this, but under what conditions you always have a map from C to its localization? Assume whatever you want. Under what conditions that has a left adjoint?
I have a localization from C to D, right? And then you're asking when does it have a right adjoint, right? Because that's
I want a
when it's
left adjoint or right?
so if I have a
If you make it
localization,
reflective, yeah.
if I have a localization and that functor has a fully faithful right adjoint, I call that a reflective localization,
Yeah, right adjoint, that's what I mean.
right?
Under what condition?
Are there any conditions? I don't know. Certainly there are a bunch of necessary conditions, right? So you have to know how the limits and colimits in D are computed in order for that to be reflective, right? Because by that result. But are there sufficient conditions? I have no idea. Uh, well, that's not true. I know. Um, I don't know what I know.
Okay.
I'm not sure. I'm not sure.
Okay.
Maybe we can talk about it afterwards, but I'm not sure. Um, okay. So let me do one sec. Uh, okay, sorry about that. All right. All right, so now let's talk about locally presentable categories. So I've always found this, I found localization, set theory, locally presentable categories. I've always found this to be hard to learn, and that's why I wanted to talk about this. Not necessarily because there aren't good resources, there are, especially for locally presentable categories. There's a really wonderful book by Rosicki. Um, but I still found it hard to learn. Okay, so I found it hard to understand the context for a lot of these things. So I want to try and talk about some of that here now. So what I want to do is start um, by looking at some properties of the categories of sets. So locally presentable categories motivate this by abstracting certain properties of set. Um, so suppose that S is a set and let sub thin of S be the poset of finite subsets of S. There is a inclusion diagram right? And then the claim is that S is the colimit of this diagram. Okay. If I have a set, any arbitrary set, I can look at all of its finite subsets, right? So this could be a huge collection of finite subsets. If I take the colimit of all of that post set of finite subsets, the colimit will be S. So let's prove that. So first of all, I have a cocone. Lambda over from I to S, which is just the inclusion. I have lambda A from A to S, which is just the inclusion of a finite subset into S. If lambda prime is another cocone, so I guess I'm doing two proofs for you guys today. Then we can define a map from S to T by sending X in S to wherever lambda prime sends the finite subset X into T. Right? So imagine I have all of these finite subsets of S, and suppose I had another cocone. Suppose I had a cocone T, looks like this. Well, in particular, singletons are finite subsets, right? So that means I have to know where to send a singleton into T. But then to define a map from S to T, all I have to do is define it on the singletons. But I already have a cocone, I'm done. Okay. So that means that every set is the colimit of all of its finite subsets. This is the property I want to abstract for locally presentable categories.
And this is a filtered colimit, right?
This is a filtered colimit, exactly.
Could you just remind me, because you've said it twice, I've heard a term from, but what is definition of filtered colimit again? I just
Don't worry, we're
remember.
getting there. We're getting there. I'm not going to leave you hanging. So this is the property we want to abstract for locally presentable categories. I'm also going to just say this remark in words. There's been a recent movement by Jacob Lurie to just call these presentable categories. And I prefer that, but I think locally presentable categories is quite entrenched in the literature. So oftentimes you'll see locally presentable, but maybe in the homotopical literature, you might see presentable category. Okay, so just be aware of that. Okay, so now let's start satisfying Ray. So the first thing is we say a poset I is finitely directed.
Well, that's right. It's filtered as in filtration. Okay, sure.
Yeah, if it's non-empty and for every pair of elements there exists another element such that X is less than Z and Y is less than Z. So that means every two elements in my post set might not be comparable, but there's always something where they move up to. Okay. So the way I
Right,
like
or
to
as a lambda calculus, you'll call it they're confluent.
they're confluent. Yeah, something like that. So I like the way I like to think about finitely directed post sets is to think that they're moving in a direction, right? They're moving towards something, right? It is like flowing in one direction. Okay. So in particular, the finite subsets of a set is a directed subset. It's a directed poset, finitely directed. Because if I have A and B in finite subsets, then of course A union B is a finite subset. And A is less than A union B, B is less than A union B. Okay. All right. And then similarly, we can generalize this from finitely directed to kappa directed. Which says that every kappa subset A of I has an upper bound. And then we say it's directed if it's kappa directed for some kappa. Okay. What else do I want to say?
In elementary math, the directed sets are used to define direct limit and inverse limit.
Right, exactly. Okay, so now, given a category C, with a full subcategory C0, we say C is generated from C0 by finitely directed colimits if every object U in the big category C can be written as U is a colimit di, where I is an I, where D lands in C0 and is finitely filtered, is finitely directed. So I want to know if I can write the objects in my category as these finite directed colimits of any diagram. So the example, of course, is set. Set is generated by finite directed colimits by thin set. So we have this large category. Large categories are annoying to deal with, but we have a small category that generates it by colimits. Okay.
Right. So intuitively, all the big things are made by, yes, gluing things in the small category together.
Exactly.
Really obvious.
Now here I said some colimit, some diagram. Now it's going to turn out that you can actually restrict to a very specific diagram. Let C be a category, C0 a full subcategory. For U in C, consider this functor. So this category here, this is the comma category of all morphisms from C to U, where C is in C0, right? And it takes this to just C. Okay. So U is an arbitrary object of U, is an arbitrary object of C, and you're looking and you're probing it by things in a smaller category. So you're not allowed to probe it by all objects in your category, but only the ones in C0. So this diagram always exists. We call this the canonical diagram of U with respect to C0. We say that C0 is dense in C if every object is the colimit of their canonical diagram with respect to C0. So that would look like U is a colimit over all objects, all morphisms, where this is in C0 of A. Okay. So the main example is if C is small, consider the pre-sheaf category on C and think of C as a full subcategory by the Yoneda lemma, by the Yoneda embedding. Then every pre-sheaf is a colimit over all of its maps from representables. This is called the co-Yoneda lemma. Okay, so this is the result that you'll hear people say pre-sheaves are colimits of representables. Okay, and in fact, they're the colimit of the canonical diagram from representables into the pre-sheaf, right? Because by the Yoneda lemma, a map from a representable into my pre-sheaf is the same thing as a section, a point X in X of U. Okay. Okay. So, okay. So, before we wanted to generate our category using finite directed colimits, but now we were able to now we considered restricting from all diagrams to canonical diagrams. So small issue. This category is not a poset in general, right? So we have some big category. We want to understand when it's generated by a small full subcategory. And it would be really nice if they were all generated using the same diagram, if they were all generated by the canonical diagram. In other words, we want to know when a large category has a dense small category. Okay. But we saw that set has a special property that not only can we do it with the canonical diagram, we can actually do it with directed colimits. But the problem is that if we want both density if we want density, we don't always get directed colimits. Okay, so this requires us to extend the notion of directedness to categories. So a small category C is finitely filtered if every finite diagram D from I to C, so I has a finite amount of objects and finite amount of morphisms. If every finite diagram has a cocone. Okay. So a filtered poset is exactly a directed poset. A poset is filtered if and only if it's directed. Okay. So filtered is a generalization of being directed to having a category rather than a poset. Okay. Good. Right. So what do I want to say here? I'm trying to figure out. We only have 10 minutes until 11, so maybe let me skip some of this stuff. Um, okay. So what do we have so far? We have a notion of what it means for a small category to generate a large category in a canonical way. We call that density. So that means that every object in your category, we can understand it using only the maps from a smaller category, right? Like as long as we hom into it from the smaller collection of objects, we can understand it just using a smaller collection of maps, right? So that's a generalization from set. And then the next generalization we want is we want to know what it means to be a finite object in a category. Okay, so definition. We say U is finitely presentable if for every finitely filtered diagram, the canonical map tau from the colimit mapping into some di and the map from U to the colimit is an isomorphism. So we say an object is finitely presentable if when I map into a filtered colimit, I can pull the colimit out. That means I map into it. That means I factor through some object in the diagram. Okay. So let's see why that makes sense. Um, so, right. So consider set. So suppose I have some set S and I'm mapping into some big colimit of sets, right? Now, if S is finite, then each element here, each element there goes to the colimit. Yeah, how do I want to say it? I think it'll actually be better if I just do the following. What you can do is notice that set has a special property, right? So That means S is the coproduct of a single point, right? So therefore, if S is, so we want to show, so if D from I to set is a filter diagram, then I have this colimit. That's the same thing as set of the sum I equals 1 to n of this colimit. Which is the same thing as just a product. Colon GI, right? But the set of functions from a point into a set is isomorphic to that set. So this is just the product. This is just colon of D. And now there's a fundamental fact that in set, finite limits commute with filtered colimits. Okay, so this fact is super fundamental. I use it like 100 times in my notes. So from that, you can switch the colimit out here like that, and then that, same thing as this. Okay, so if you're a finite set, then you're finitely presentable, and then vice versa. So remark, set objects in set are finitely presentable if and only if they're finite. So finite sets. Okay. Good, good, good. All right, now we finally get to the definition. A category C is locally finitely presentable if one, it is co-complete, and two, the category CFP of finitely presentable objects in C is essentially small and dense in C. So a category is locally presentable if it's generated by its finitely presentable objects. Okay. And it turns out, I'm not going to write this down, but you can look it up in Rosicki's book. If you are co-complete, then an object can be written as some filtered colimit of presentable objects if and only if it can be written as a colimit of its canonical diagram with respect to the presentable object. So it's a very interesting fact, and it really simplifies things a lot. So there's no way to kind of get away from this idea of this canonical diagram generating your objects. Okay. So now let's skip right to the big result here that I wanted to talk about. So if C is a locally presentable So I say it's locally presentable. I talked about locally finitely presentable. You can talk about locally kappa presentable, and then being locally presentable is being locally kappa presentable for some kappa. Okay. So if C is a locally presentable category, then the functor so what does this functor do? This is not the Yoneda embedding. What this does is it says, okay, I take an object U, I take an object U, and I send it to the set I U, where I is the inclusion from C0 to C. So it's not a pre-sheaf on C, it's a pre-sheaf on my smaller category. I'm only allowed to hom into it from things in the smaller category. Okay. If C is locally presentable, this functor, so let's set C0 equal to CFP, these are the finitely presentable objects, is fully faithful. In other words, C is a reflective localization of a pre-sheaf topos. So I have C, I have Y0 from the pre-sheaves on the finitely presentable objects, and it has a left adjoint. Oh, I'm sorry, I forgot to say. The left adjoint always exists, but it's not always fully faithful unless, oops. So being locally presentable tells you that this left adjoint, that this thing is fully faithful. So that means that this is a reflective localization. This gives you a reflective functor. Okay. And furthermore, Y0 preserves filtered colimits. All right. I'm going to try and wrap this up in 15 more minutes. I'm going to do my best. Okay. And then theorem from this, a category C is locally presentable if and only if it is a reflective localization of a pre-sheaf topos. So that's another way of defining a presentable category as one that's a reflective localization of a pre-sheaf category.
Right. So you're telling me, in fact, yes, you got this construction, but in fact, they're all that. Yeah.
Yeah.
So,
and presentable categories have really nice properties. So nice properties. If F is a functor where with C and D presentable, locally presentable categories, if F preserves colimits, it has a right adjoint. So that's a really nice thing. And how do you prove that? Well, first you show that this is a reflective localization of a pre-sheaf category. You prove it for pre-sheaf categories, and then it implies it in general. So this is an incredible theorem that works for presentable categories. Okay. All right, good. So we did that. Now, so a presentable category is a localization of a pre-sheaf category. Now, it turns out that whenever I have a site.
So we always know that left adjoint preserves colimits, but this is the kind of the inverse.
Exactly, right? So there's like the adjoint functor theorem, right? Which is really a pain in the ass to use because you have to have all these special annoying things you have to check. This says no, you don't have to worry about any of that. If it preserves colimits, it has a right adjoint. So it's a beautiful theorem. But it only works with the locally presentable categories. Okay. Now, so now, suppose CJ is a small site. Oh, sorry, that's not what I wanted to say. Now, suppose E is a full subcategory of a pre-sheaf topos, and it is and furthermore, it's a reflective subcategory. So that means that it's a locally presentable category. Yeah, what do I want to say? If L also preserves finite limits, so this is sometimes called a Lex localization, then we can craft a coverage from L. So how do you do that? So I said before, maybe last time, if you have a coverage, you can define what it means to be a local epimorphism, right? So once you have a coverage, you know what it means to be a local epimorphism of pre-sheaves. You can also define a local isomorphism of pre-sheaves, okay? So anytime you have a coverage, you have a notion of a local isomorphism between pre-sheaves. A local isomorphism you can think of as something like a weak equivalence, something you want to mod out by, right? You want to localize that. Okay. So the local isomorphisms of a site have certain properties that you can characterize abstractly. So you say, oh, a class of local isomorphism satisfies this, and this property, right? Turns out to every class, every system of local isomorphisms, you can get a coverage from it, and then vice versa. So every coverage induces a class of local every class of local isomorphisms induces a coverage, and in fact, it'll be saturated, and that's a bijection. So what do you do here? You say, okay, I have this functor L, and I want to look at the class of morphisms that are inverted by L. That will turn out, if L is Lex, if it preserves finite limits, the class of morphisms that are inverted will turn out to be a class of local isomorphisms. So let me just write that. So if L is Lex, then L inverse of the isomorphisms in E is a class of local isos, hence hence get a coverage, which I'll call J of L. Okay. And now we can finally say the Little Giraud theorem. Little Giraud theorem. And this says if epsilon E is a Lex localization, say Lex localization, then there exists a coverage on C such that E can be recovered as the sheaves on this on the original category C here with this coverage you get from the localizer L here. In other words, so corollary, Grothendieck toposes are precisely Lex localizations of pre-sheaf categories. So locally presentable categories are precisely the reflective localizations of pre-sheaf categories, and Grothendieck toposes are precisely the Lex localizations of pre-sheaf categories. Okay. And so fixing any small category to obtain a sheaf category on it, you can either give a saturated coverage, a Grothendieck topology, a class of local isomorphisms, or Lex localization. So this ties everything we've talked about together. So saturated coverages, Grothendieck topologies, class of local isos, Lex localizations. Of pre-sheaf topoi. These are all in bijection. And they all describe all the possible sheaf categories on a site. So I did want to talk about Giraud's theorem, but I know I'm running late. So what do you think, Mamu? Do you want to hear about it, or are we good?
Let's say you have 6 minutes before I go to my other meeting.
Okay. So then I'll just say in words what Giraud's theorem is, because that was the little Giraud theorem. This is the big Papa Giraud theorem. And it says, if C is a locally presentable category and it has disjoint coproducts. So I'll explain what all this means in a sec. Universal colimits and effective equivalence relations. Then C is a Grothendieck topos. So we saw before that there's almost like the small little difference between presentable categories and Grothendieck toposes, which is one's a reflective localization, the other one's a Lex localization, right? And then Giraud's theorem tells you precisely how different locally presentable categories are from Grothendieck toposes. So if you're presentable and you have disjoint coproducts, which means that that this is a pullback where this is the initial object. So that means that whenever you take a pullback of inclusions into a coproduct, you always get the initial object. It having universal colimits means that I can pull back colimits. Like say I have a push out, right? And then I pull back everything along some morphism and I get a new square, and I want that thing to also be a push out. So that would be like having universal push outs. But here I want all colimits to be universal. I want to be able to pull back all colimits. And then effective equivalence relations, maybe I won't get too into that. It's a special property of certain sub-objects in your category. If all of these things are true, you are a Grothendieck topos. You are equivalent to a category of sheaves on some site. Okay.
What a beautiful theorem.
It's an absolutely beautiful theorem. And there's just one last thing I want to say, which is the following, that you can repackage all of this into another statement. And that other statement is called weak descent. So what do I mean by that? So can package these properties together. So it says, suppose I have some diagram and I take the colimit, right? And then I take the slice category over that colimit. Then what I can do is look at is I can take this colimit, this thing is glued together by these pieces, and I look at a map into this big glued together thing. Then I include all of those pieces into it and I take the pullback. So in other words, I have something mapping into a glued together thing and I piece it and I pull back everything. And now I have this thing is a whole bunch of pieces here. And I want that thing to be a colimit now of the original object. Okay. In other words, I want there to be some kind of equivalence, which I'm not going to go into details here, precisely what this means. I want there to be some kind of equivalence between the slice over a colimit and whatever this notion of like a two categorical limit of these slice categories is. However, this is too strong. This is too strong. Sorry, just give me 1 second here. Set does not satisfy this. It satisfies a weaker condition. So let's call this descent, which means that if I map into a colimit, I can pull it all back and I'll get a colimit of the thing I'm mapping into it. Set does not satisfy this. It satisfies a weaker condition called weak descent. So that means that Grothendieck toposes, they don't satisfy descent, they satisfy weak descent. However, so last remark, if we consider infinity categories, an infinity category, so this is Lurie, Resk, Giraud, Toan Vasozi, whole bunch of people contributed to this. And I'll say this is the last theorem, actually. Last theorem. An infinity category. Just make sure I'm saying the right thing here. Is an infinity topos if and only if it's locally presentable in, some infinity sense, and it satisfies descent. This kind of descent, where here everything is infinity. That's it.
Not weak descent.
Not weak descent. So you're an infinity topos if you're presentable and you satisfy descent. So you can see that going to the infinity world makes certain statements like this just unbelievably clean and simple. And the whole idea is that when you do a colimit in sets, you lose information, right? Yeah. And then when you pull that information back, you might not get everything you started with.
Yeah.
But if you take spaces and you take infinity colimits, you retain all of the information. You don't lose anything.
Yeah.
And you can reconstruct the thing that's mapping into the colimit from those pieces, and you can get it exactly.
Because colimits in sets collapses too many things.
Exactly, but not in spaces. In spaces, colimits is like taking like a groupoid,
Sure.
right? Like you don't just take an actual quotient.
Yeah.
All right.
You sort of moved in all the information you would have lost into the higher morphism.
Exactly. All right, and that will conclude my mini course. Thank you guys for sticking around, and thanks, Mahmoud, for
Thank you.
having.
It was really good, very
It was a
valuable.
lot of
I'm
fun.
happy. I'm happy it's recorded. Yeah.
Yeah, me too.
Yeah, thank you. I'm certainly impressed how much material you did.
I wish I could have
quite
been
a
more
quite a
honest.
job on this.
Good job.
Thank you, thank you, thank you.
Okay, talk to you guys soon. I'm gonna run to my other meeting.
All right,
And so
have a
next
good
week
one,
will be
guys.
math.
All right,
Okay.
and yeah, just send this to me when you get a chance, Mahmoud.
Okay.
All right, bye.
Bye, everyone.
Bye.